Okay, we're back with class 21, and this is the third video. In the first video, we established that there's these two Gibbs equations, and in the second video, we did a little detour into getting the entropy change of a solid or a gas with constant specific heat. Now we're going to explore into the mysteries of some of the equations that you ran across in that cheat sheet. All right, so we have some things in here where we've seen them already for various types of processes of, just constant pressure in a closed system, constant volume in a closed system, constant temperature in a closed system, isentropic in a closed reversible and adiabatic system, polytropic, isentropic, steady flow. This might not be handled in this semester. This might be something that comes up in next semester. And then the polytropic might not come true. But anyway, some of these you might have seen them already, but let's see where they came from and be able to get them ourselves, right? Not be reliant. So they come from these Gibbs equations. So first off, entropy change in an ideal gas. So one thing to remember when using this cheat sheet, these are all ideal gas based. And you'll see that a lot of them have CV and CP in various places. I'm not finding here, it says CP. So all those are always an assumption of constant specific heat, either at a constant volume or constant pressure. And also recall that they're also the assumption this is ideal gas, right? So they don't apply if you have something that varies from ideal gas, obviously a gas that varies from ideal gas, but certainly not applicable if you have a pure substance that has a vapor dome that changes phase. All right, so we're going to take this one and we're going to apply some ideal gas stuff to it. So what if I divide all this all the way through by temperature? I would get ds is equal to du t over t plus p over t dv. All right, so I have them in an ideal gas now. But now we can go ahead and use what we know that du is equal to cv dt. All right, so we can replace that up here. We can also use the ideal gas law. And we could rewrite it because we have a P over T right here. We can replace that. So if we have PV equals RT, then we can also, convert that into P over T is equal to, I get this wrong? No, it's going to be R over V, right? So replace that right there. If we do that, we will soon see that we're going to get ds is equal to CV dt over t plus r dv over v. And we know when we integrate this, these are going to be natural logs, right? Because we have dt over t, dv over v. So we can go ahead and just integrate. We don't even need to show it. And we will get S2 minus S1 is going to be equal to, and for the time being, just to be very, very specific, we don't, temperature, this CV can vary with temperature. So we're going to, for the time being, we're going to say, well, we don't really quite know because we don't have for sure the instance that this is constant. So we'll leave it as an integral still. But we will have, I guess I'll write it as dt over t, right? And we're going from 1 to 2, states 1 to 2. And then, but this one for sure doesn't vary. This r is constant, so we can go ahead and get that one, the natural log of v2 over v1. Right here. So here's one. That's an equation that we might see, and then we can further simplify some things if we have perhaps something we know about the process being constant temperature or constant volume, something along those lines. But anyway, this is equation 613 in your textbook. In a similar way, we can go ahead and divide through by temperature. So ds is going to be equal to dH over T, and minus, okay, so we're going to have ideal, well, let's go ahead and write this right here. So we'll have V over T, and then dP. All right, so we use that dH can be found from Cp dt, and we also can use the ideal gas law, rewritten as, how am I going to rewrite it? Okay, V over T is equal to R over P. All right, so you can look back up to here, and you can see that it's makes sense. We just have V divided by T, and we can replace this, and then of course we can replace that, and so we end up with ds is going to be equal to Cp dt over T minus R. All right, so we have R, and it's going to be dP over P. All right, and so in a similar way, just integrate, and we have S2 minus S1 is equal to, and this can vary with temperature as well, Cp is dt over T, states 1 to 2, and then minus R, and the natural log of just P2 over P1. All right, and so once again, that is an equation that we would find, equation 6.15. Okay, so next thing, okay, so we have to take care of some different various cases that we might run across. One of the cases in dealing with either of these two equations is we can make an assumption that this is constant, or we can find that this varies with temperature according to really essentially two separate ways. The first way is something we touched on briefly. That's fine. So let's talk about the third way we don't. So the first way, we have these different, if we have an isentropic process right here. Okay, so I want to like delay this part of it right here. We're not going to do the isentropic process just yet, but we're going to look and see if we could solve these two right here. I think on the next page we deal with the isentropic process. But let's just take a look at this. So I'm gonna cross this out. So what really matters to me right here, and I should have brought that up. So I'm glad I'm doing this video before I teach class tomorrow. Let's say so I'll write three scenarios. One is constant specific heat, and by the way, if one of the specific heats is constant, they both are, right? So because recall that R is equal to Cp minus Cv, right? And if you look it up in the tables, you'll see that this is true. So this is a good thing to recall. So if one of these is constant, you know that's constant. One of these is constant. They both have to be constant. So in this case right here, we get a delta S. I'm just going shorthand. Is Cv ln of T2 over T1 plus R ln V2 over V1. And the other equation gets us Cp ln T2 over T1 minus R ln P2 over P1. All right, and these are not process specific, but they are specific to being an ideal gas and being constant specific heat, right? So this is one approach, but you know, as we've seen previously, this is not always a proper, this constant specific heat does not always hold true. A second way to do it is that now instead of having it constant, we can have CP or CV, and I'll just use CP. CP as a function, of T. And where do we have that? Well, it's actually available in table A.6. That's supposed to be 6, A.6. And so I will remind you that's there. We don't really use this very much, or we haven't. Here's 8 to 8.5, but recall that you could get the specific heat from having this equation where we use theta. We replace theta by dividing the temperature in Kelvin by 1,000. And we have these coefficients, boom, 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 boom. But now we have CP is a function of temperature. And I'll do an example where we do that. But of course, this is not something we're not going to do this very often, but it can be done. But we'll demonstrate that it can be done. So I'll write this out here, that CP is equal to CO plus C1 theta plus C2 theta squared plus C3 theta cubed, where theta is equal to the temperature divided by 1,000. And that's in Kelvin right there, right? And then lastly, here's one that might be new to us, right? So here's something we probably won't do, but we have at least had this passed underneath our nose once, that we have a way of having, we have some curve fit approximations of a temperature dependent constant specific, not constant, but specific heat for a constant pressure. And recognize that we could also find a variation of that by taking R and just subtracting it for the CV. Did I say that the right way? Adding R. No, subtracting R. Yeah, subtracting R. Yeah, that's right. So subtracting R. So if you subtract R from this, we would get the CV instead. Here's a new one right here, that we define a special thing called the standard entropy. And it's a kind of a weird thing, but what we ended up doing is define this thing STO. Right, that's supposed to be a lowercase s. And it's defined as the integral of TO to the actual T of CP over T dt. And you're like, what the heck is that? Well, you can look this up. Look up in tables A.7, which has a bunch of subtables, and A8. Right, so we're going to see that that's, you might have noticed that was in there, but what you do now, instead of looking this up, instead of doing this integral, you can replace this thing right here with this equation right here. So we will, instead of doing this equation up here, we're going to have ST, let's say state 2, 0, minus ST state 1 minus R ln P2 over P1. Right there. All right, so here is a means when we look this thing up. So let's take a look at what I'm talking about in those two tables. You can see that they're right there. So here's 7.1, and so you can see, okay, so at a particular temperature, of course this is in Kelvin, you can look up this value right here. Right, so there you go, ST, and there's a bunch of them right here. So we can replace those things inside that Gibbs equation with this relation. But remember, we're still dealing with an ideal gas, right? So we've still, in order to get to this equation right here, that required an ideal gas assumption. So I think I have an example that comes next, and we use oxygen. So that's fun. So what's the next video is going to be?